So hello, Piotr, once again, and the title of this talk is yet another invitation to quantum game theory. Piotr, the Zoom is yours.
So thank you, Paul, for invitation for this hackathon and the opportunity to give this talk. This is a very fresh talk. I just finished my slides, so I hope there are not many mistakes there. And the title of the talk is yet another invitation to quantum game theory. You will just understand why is the reason for the title in the next slide. I work first of all. I work on AstroSand, which is a new unit of Nicolaus Copernicus Astronomical Center of Polish Academy of Sciences, and the unit and my work and the unit is supported by Foundation for Polish Science and the European Union. And I consider this talk as a part of my job and popularization of science. Why yet another introduction? Okay, or invitation. The reason for that is that my mentor in the at the beginning of my career, Jan Słatkowski, published a paper in 2003, an invitation to quantum game theory, which was pretty interesting, and at least for me, it was a way to start working in the subject during my PhD thesis writing times. So you can read the motto of the paper, which I find very amusing. The man was very appreciative but curious. He asked the farmer why he called his horse by the wrong name 3 times. The farmer said, "Oh, my horse is blind." And if he thought he was the only one pulling, he wouldn't even try. So that's in a way a representation of game theory that we are agents, horses in this case, which are blind, which means that we do not know the actions of other horses, other agents, and we have to make some decisions which um lead to an outcome. And of course, depending on our decisions, our strategies and outcomes are defined by a game. So let me just introduce the first idea, a prisoner's dilemma, which is a very traditional game, strategic game, very well known, and probably you've heard it about already somewhere. But for some reason, I would like to present it once again because later I will show you how this game can be quantized and what is the result of quantization. First of all, okay, maybe I haven't told it precisely, but we are talking here about game theory, not like computer games, not video games, but game theory, which means how rational agents behave given um, the strategy um, sets. So what it means. Let's see at this example. We have two players here, Alice and Bob. Alice has two options, C and D. Bob has two options, C and D. Alice and Bob obtained a reward or some payoff depending on the option, which we call strategy. What means C and D? C is cooperation, D is defection. The story behind this game is such that we have two prisoners which are locked in two separated cells. They cannot communicate, they cannot share any information between themselves, and they have to decide whether they want to cooperate with each other or defect, which means cooperate with the authoritarian system that keeps them in the prison cell. The payoff is such that, of course, what is the goal? The goal want to maximize their own payoff. They want to be the best off from given the situation. So how we read this payoff? 3-3 means that if Alice cooperates, Bob cooperates, Alice will obtain 3 units of whatever, and Bob's will obtain 3 units of whatever. We can imagine here that it is the reduction of time in the sentence. Well, let us imagine that they are, let's say, uh, accused of a crime, and they can expect to have 6 years of punishment in the jail time. But they can be the jail time can be reduced by a given amount, given number. For this case, it will be 3. So they will spend less time in jail. If they both cooperate with each other, they will spend 6 minus 3, only 3 years in jail each. But there's other option. Alice can cooperate and Bob can defect. In this case, Alice will gain nothing, so she will spend like 6 years in the jail. But Bob's sentence will be reduced by 5 years, so then he will spend only 1 year in the jail. And symmetrically, there is the same for Alice, 5 and 0. And if they both defect, they will spend 5 years, 6 minus 1 years in the jail, both, each of them. So look, what is the rational thing to do? Let's analyze it. Let's look at the Alice payoff only. We don't care. I mean, we do care about Bob, but we are looking from the point of view of Alice. So Alice can obtain 5, which is large, or 1. So if she cooperates, her payoff will be 3. If she defects, assuming that Bob cooperates, her payoff will be 5. So 5 is larger than 3. So she has incentive to say 5. So to choose 5, which is strategy defect. In this case, if Bob's defects, she can obtain either 0 or 1. If she cooperates, 0. If she defects, 1. So in both cases, she is better off by choosing defect. It is the same for the Bob, of course, symmetrically, because the game is symmetric. So what is important that, okay, it is reasonable for them to choose cooperation and cooperation, to cooperate together and to obtain smaller jail sentence. But unfortunately, due to this fact that when they only look at their own payoffs and don't know the strategy of the other player, they will always move toward defection. It is in a way the outcome of this game with irrational agents would be 1-1. So the payoff will be smaller for both of them. We call this situation Pareto optimal strategy because they are better, both of them are better off. And this situation, Nash equilibrium. In a way, a Nash equilibrium is the outcome of the game given the rational players and of course the reward structure or payoff structure for the game. And it is an interesting example that people were studying for years, and there's entire field that study this kind of games. These numbers RPTS are called reward, punishment, temptation, and sucker's payoff. So there's entire language about it, and you can play with these numbers, and then the situation changes depending what is the relation between these values, of course. Okay, so we have an example of strategy game. You know what is a payoff. You know how to analyze this kind of games. Let's move to a very simple example of a very simple game called penny flip game, and its quantum version. Now the story is slightly different. There are 2 players, Alice and Bob. There's a penny, so a coin, hidden in a box. The players can flip the penny or choose to not flip the penny. Those are the actions. At the beginning of the game, the penny is faced up. So face heads up, let's say. The game goes as follows. First, Alice puts her hand into the box and chooses to flip or not flip the penny. Next, Bob chooses to flip or not to flip the penny by putting his hand into the box. And at last, Alice plays last and chooses to flip or not flip the penny. Of course, Bob and Alice are not aware of the other person actions. At the end of the game, so after 3 moves, the penny is revealed, and Alice wins if the penny is face down. Otherwise, Bob wins. So it's a strange game, but for some reason it is interesting and important, and I will show you later why. Uh, yeah, so because the game, the players have no information about the other person actions, basically there is no way to win in this game for any of them. So the 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 probability of winning is basically 50-50, assuming they will play randomly just by applying random moves every time they put their hand into the box. The gameplay of Matrix is for Ali's point of view is this one. So if there is no flipping at all, the penny started up, and Alice wants to needs to have this penny to be down. So the Alice wants -1. So for non-flipping, doesn't nothing happens. If the penny is flipped only once, of course Alice wins. If the penny is flipped twice, Bob wins. If 3 times, Alice wins once again. So the payoff at matrix is like that. This is a zero-sum game, therefore we do not have to show the matrix for Bob because it is just a negation for of this one. Okay, yeah. So the game classically is not very interesting, but let us assume that we can play this game on a quantum device. Let's say quantum computer, and there are two parties having access to this quantum computer. But as we will reveal later, only one paid party is trained in quantum computation, then the other is not. So let's assume that we have a qubit. Here it is denoted by like this C. Uh, Heads up or penny being up is denoted by 0. Being up down is denoted by 1, or tails up as 1. Then of course, we can introduce flip operator, not flipping operators, or matrix, which is flipping is just negation, not gate, or sigma x, and not flipping is just identity, or yeah, identity. We do not do anything with the qubit. Okay, so the winning condition here is given by the expectation value of sigma z operator in the final state of the system. Denoted here C. Maybe it's slightly confusing that it's C and C. Okay, it's a big word from quantum mechanics, but what it means, we just take the probability of obtaining measurement 0 times 1 plus the probability of obtaining measurement 1 times -1, which is exactly the same. Okay, in this game is just a faithful representation of the previous game, or it's just implementation on a quantum computer of the previous game. It is not very particular interesting. We just use a qubit for rather than a penny, and the results will be the same for the qubit as for the penny. Okay, so now of course we are in a quantum world. We can do quantum actions, which in this particular means that we can apply, for example, Hadamard gate. And let us assume that only Alice knows that uh, how to operate a qubit properly. So she's able to apply the Hadamard game, and Bob is not trained quantum computation. He doesn't know how to do it. Then what happens? Okay, Alice can apply her Hadamard gate on the initial state of the game. Um, then Bob can flip or not flip the qubit, but it doesn't matter because the eigenstate of the oh, because the zero state transformed by Hadamard gate is then eigenstate of the flipping operator. So negation. Therefore, nothing will happen, and then Alice can recover the initial state by applying the Hadamard gate, and she's done. As you can see, there's a minor issue here. I believe that we should start with 0, but it doesn't. With 1, but it doesn't matter so much. Maybe there is a small mistake here. And of course, if uh, Bob applies negate, do nothing, do not flip the gate, and which is identity, Hadamard identity, Hadamard is just identity, so nothing happens, obviously. Okay, sorry for my non-Polish audience, but this is a visual representation of this procedure that is in a comic book we produced jointly with a couple of people. And it is an explanation of this process in a nice graphic form. So I wanted to show it. Unfortunately, it is only in Polish. We are looking into possibilities, opportunities to translate this book into English. So we start with 0, of course, and we have a qubit in the box here and 2 players, Alice and Bob. And of course, Alice can play any of the classical player. Bob, the classical player, can apply identity, so nothing will change, or X he will flip the qubit from 0 to 1. Okay, we have 3 stages of the game, and then there's measurement. That is what is set here. So of course, in the case of the quantum player, she can Alice here can apply this Hadamard gate, which is just transformation from 0 to the state plus, which is like 0 plus 1, of course, and therefore I or X, which is a rotation, doesn't around the this axis X, this rotation around this axis, doesn't change the state. Therefore, nothing will happen, and of course, Alice can recover the initial state by applying Hadamard. Yeah, so there's a magical move. This move can always give Alice an opportunity to win, which is in the comic book pretty important. And for the Polish speaking people, I will provide later the link for the story. Okay, so in the past, and as you can see, 10 years ago, we published a couple of papers discussing this game in various scenarios where we, in a way, assume slightly different rules of the game, but also assume discuss implementation of the game on a real quantum device. I mean, still imagine, but nevertheless, quantum device, but that is driven by some Hamiltonians. So you can refer to this paper and look at this paper, how one would implement this game on a quantum device and how implementation of this game can be exploited by a player that understands how the implementation works in order to always win, even if the both players are quantum. But one is better trained and knows more about the device, so the other one is not trained so well and he doesn't know how the device exactly works. Um, there's another paper in which we assume that device is not perfect and analyze this situation just by looking whether what happens if the system decoheres and the quantumness of the system is destroyed with time. So how quickly you have to play this game in order to have some chance of winning on an imperfect device. Okay, so now let us discuss prisoner's dilemma with quantum resources, which means players being able to share, to not communicate, but to live in a in a world that they when where they can share entangled quantum states. So this is idea published in a very famous paper, Quantum Games and Quantum Strategies by Jens Eisert, Martin Wilkens, and Maciej Levenstein. Uh, as you can see, a couple of years ago, it was submitted for the publication in 1998. It's a very nice and elegant paper, which is might be slightly difficult to read for newcomers to the field because they use maybe more physics related language than the language that is related more to quantum computing. But I'm going to use this language in order to give you an introduction to this paper and the summarization of results. I encourage you to read this paper because if you are interested in quantum game theory, because of course it's one of the most important in the field. I mean, it's not so difficult if you understand quantum computing. So here we have a setup, which is the figure is taken directly from this paper, where there are now prisoners. Prisoners share qubits, and prisoners cannot communicate. There's no communication between them, but the prisoners' qubits are entangled using a quantum 2-qubit gate. Then so the prisoners are given the state after the qubits were entangled by this J operator, and they can apply their actions. So actions, unitary gates, unitary operations. Then the system is disentangled by the uh, gate that is conjugated to the entangling gate, and the system is measured. And we consider the measurement outcomes as their actions, so operation or defection. So once again, they start with disentangled qubits, separated qubits. They are the qubits are being entangled. There are unitary operations, which are the actions, disentanglement, and measurement, and then decision. Okay, so now there's the mathematical part, which is okay, slightly complicated, but I'll try to explain it as best as I can. So the final state of the game is given by the first equation, where rather than, as you can see, rather than they using 0 and 1 as our labels for the states of the qubits, they use C and D in the paper. So you can just map C to 0, D to 1, or whatever. It doesn't really matter. So we start with two separate qubits in state C. Then there's this J entangled gate, unitary operation, and J dagger, the disentangling gate. So that's the final state of the game before the measurement. The the entangling gate is given by this matrix. So this is exponential of D. D is this spin flip, so-called spin flip matrix. And there's a parameter gamma here, which you can tune in order to have more and less entanglement. When gamma is 0, obviously this J operation is separable, so this operation cannot create entanglement. If gamma is greater than 0, then some entanglement or even large amounts of maximal entanglement can be produced, and maximal is for pi over 2. Um, And of course, you can verify it using some simulators or QSKit or whatever tool you like. You can verify it if you are able to implement this gate using elementary 2-qubit operations or 1-qubit operations. It is possible. It might require some specific work. So for the actions or strategies of the players UA and UB, we choose two matrices, D and C. C is just identity D. I already explained it. The payoff from the point of view of Alice, and of course for Bob is similar, is given by this nice equation, which is also expectation value of the sigma z operator in state psi f, but using just plain language, it is probability of measuring outcomes in CC times 3, because that's the value of a cooperation strategy. DD1 with defection, um, DC is 5, and CD is 0. So basically, that's the strategic the payoff matrix is encoded here times probabilities, because of course we're in quantum world, so everything is a quantum is probabilistic. Therefore, we have to deal. We want to measure probabilities, and p this okay. So sorry for the mistake. It's p of sigma sigma prime should be here. So basically, it is just this overlap. So the final state, which is here, with cc prime, which means sigma sigma prime, which is c or d. That's just placeholder for symbol c or d. Okay, so that's a faithful representation of the classical game, assuming that gamma is equal to 0. So if gamma is equal to 0, it's basically a quantum implementation of the classical problem I presented to you at the beginning of the presentation. But of course, now we are in the quantum world, and we are allowed to do movements which are quantum. For example, we can apply this Q gate, or if both of the players apply the Q gate, and assuming that they share entanglement, that the entanglement is maximal, the strategy QQ becomes a Nash equilibrium for the game, and it is Pareto optimal at the same time, which means that the situation is completely different. It means that now the game becomes okay, let's use this word, fair for the players. So they can there is no incentive for them to defect. They can cooperate, and they payoff will be maximal for each of them. So this Pareto optimal. Why is it interesting? Because okay, prisoners the dilemma has many interpretations, and like it is discussed in economy, in politics, in many applications. But here, what you can see is that the players do not communicate. Their actions are independent. In the meaning of the word communication, independent, they do not communicate. But because they do share a quantum state, they can do better than classically, which is an interesting result of this entire endeavor. And in the paper, the original paper, you can look at the how the situation changes, so when there is more and less entanglement, and where these payoffs values are different. So there's entire analysis of this in this paper, when you can look at the landscape of the on the of this problem. And it might be an interesting task to implement this problem on a quantum computer and play with it. Okay, so the last game I wanted to discuss is Magic Square game, which is a class of games called quantum pseudo telepathy, which of course the name is very nice and interesting, and therefore it attracts a lot of attention sometimes, sometimes too much. I was approached by a couple of weirdos because I published some works on this subject. Okay, what is the issue here? So it is a Magic Square game, which means that okay, we have Magic Square. What is a Magic Square? The Magic Square is a 3 by 3 binary matrix filled with okay, zeros and ones, of course, this binary, and we want this matrix to have rows summed to 1 or in even number, summed in the uh, terms of Z2 addition in the Z2 field, or and columns to sum to 0 or to be uh, odd. Oh, is drunk. Okay, so the columns to sum to 0. Sorry for some mistakes here. Yeah, so the idea is rows sum to 1 modulo 2, of course, columns to 0 modulo 2. Of course, such an square does not exist. That's the reason why it's magic. So there is no way to fill this square in such a way that these conditions will be fulfilled. There will always be one row and one column that does not, where you cannot fulfill both of the conditions at the same time. Okay, so now there's a game that in a way is related to this problem. Once again, there are two players, Alice and Bob. Alice is given a number of the row. Bob is given number of the column. The goal of Alice is to give the entries for this row, and the goal of Bob is to give the entries for this column. And of course, we expect that the parity conditions are met. So the situation changes. There are only 2 rows and 2 columns, but so therefore we don't care about other entries, and and only care about the sums in rows and this particular row and this particular column. So the parity conditions. Um, of course, we want them to give the same number for at the intersection of the row and column. Alice and Bob are allowed to prepare their strategy, so discuss their strategy in advance, but they are not allowed to communicate during the game. So there is an arbiter, a person from outside, that gives them the task, so row and column. They can, not knowing before, of course, what row and column they will be given, they can choose a strategy, and then they have just fulfill these conditions. Okay, classically, what you can do the best is obtain the probability of winning, assuming, of course, that the rows and columns are given uniformly to you 8/9. So because of this limitation that you will have always one entry that doesn't fulfill your strategy, they can prepare an imperfect magic square in advance and use it for as their strategy, but sometimes they will be given a row and column that they cannot fulfill the condition for them, and they lose. But there is a quantum strategy, of course. uh, so assuming that the parties are allowed to share entangled states, in this case, 2 pairs of two entangled qubits, they can achieve the probability of winning one. So win, in other words, win always. So the state, for example, can be such as here, which is basically slightly modified to Bell pairs. And there is a collection of matrices that implement the strategies they can uh, apply to the qubits jointly, um, depending on the row and column they are given. So those are matrices for Alice, those are matrices for Bob, and of course 1, 2, 3 denotes the row and column they are given, and row in case of Alice, column in case of Bob, as far as I remember. And of course, uh, we just assume that Bob does not change the system of Alice directly, and Alice does not change the system of Bob directly. So they can have share these two qubits, apply these matrices, measure the outcome, measure the state they have in the final state they have, and look at the outcomes at the zeros and ones. They obtain 2 bits of information, but because they know that there are these conditions, parity conditions, they can calculate the remaining third bit from the parity conditions and return these bits as results. And therefore, and as you can see, you can play with that. They can always win, and the strategy in a way is perfect. Which is interesting because here the problem is even more interesting that in case of the players of the prisoner's dilemma, because there's an interactive uh, part of the problem that they have to solve. They are not, because in case of prisoner's dilemma, of course, the classical prisoner's dilemma, the players could, in principle, decide that they want to cooperate to have better outcomes, um, to achieve better outcomes for themselves. And they can assume this strategy, and if they use this strategy, they will, in a way, win. But here is a different problem. They do not have the information about the game before the game starts, all the information, because they don't know the questions that were given. So the rows, the number of the row, and number of the column, which is even more interesting, that you can have this interactive game that classically doesn't allow you to win, but there's a quantum way to win this game always, even in this interactive case. That's the reason why it is called pseudo telepathy, because they can coordinate jointly as if they were able to communicate jointly, so between each other. But it is not the case. They cooperate without communication, which is a feature of quantum information theory, which is very unintuitive. From a layman's perspective, this looks like communication, but it is not. There is no information shared between them. They just share a quantum entangled state. Okay, so that was a problem I was investigating during my early scientific times with my colleague Jarek Miszczak. Probably some of you already know, of course, and our mentor Jan Słatkowski. Many years ago, we were adding some noise effects, and we were looking whether this how this game behaves when the entangled state is not perfect, and when we lose entanglement, and there is some noise added to the system, how the game behaves. Later, with my another colleague Zbyszek Puchała and my PhD student at the time, we were investigating how you can fight this noise under some assumptions. So there is a noise, but what you can do the best to fight it, and how can you enhance the quality of your probability of winning, or the quality of your result given a particular implementation of a system of this noise system. Uh, and there is another paper which is like a little bit funny. We were investigating what happens if you play this game in a relativistic setting, assuming so-called Unruh effect, which is a physical effect that is postulated but not proven yet. So assuming that two players are in different relativistic systems, and one of the players is moving in an accelerating frame from the another player, what are the best results they can achieve in this game? So basically, how the entanglement of the system changes, and the probability of winning decreases with rising acceleration. And at the end, I of course wanted to show you our comic book, which is shown here, which is only in Polish, unfortunately. Now we are looking for the opportunities of translating this into English. This is the first edition, the cover of the first edition, and the first edition is available online. You can download it from the link at the bottom. The second edition, enhanced edition, where Piotr Biskupski is also involved, is will be soon available on the market. I already have some prints in my office, so you can buy it in Polish and in English. Unfortunately, not yet, but hopefully, maybe in a year, it will be available. You have all the ways to contact me. I will be looking for a postdoc that is mostly skillful in deep neural networks to work on dark matter detection and gravitational waves detection. If you are interested, please contact me. It is not official yet, but I would like to just tell you about it if you are interested. You need, of course, to have a PhD in computer science, physics, mathematics, maybe. So thank you. That's my slide, and I welcome any questions you have.
Okay, great. Thank you, Piotr. Thank you very much. Very nice, very interesting talk. Are there any questions to Piotr? I can see that there was a question about the title of the paper that was presented earlier. So I think that it was Quantum Games and Quantum Strategies. Is this correct?
Okay, sorry. Is it? Can you? Oh, I lost the. Can you see the presentation or not?
Yeah, we can still see your slides.
Wait, can I see them? Okay, so maybe.
Yeah, yeah. But anyway, I think that Antonio has already answered on our chat, so it's clear
Oh,
now.
okay.
Right. Thank you.
Uh,
Are there any more questions, Piotr? Last chance.
yeah. Questions can be not directly related to the topic.
Yes, there's a question if we'll have access to slides. Can you share the slides with us as well?
Sure. Maybe I will spend some time to fix them,
Yeah.
because I see there are
Okay,
some
no
minor
worries.
mistakes.
So for sure there will be also video recording available on our YouTube channel. So we'll share it as soon as it's ready. But maybe Piotr will be also able to just share the slides on our Discord. And as Piotr said, you can also ask some questions not directly related to this talk. So Piotr is a very experienced researcher in the domain of quantum computing and machine learning as well, and quantum machine learning. So maybe you have some questions regarding these domains or developing quantum games in general, then this is a great opportunity. There are not that many experienced researchers around. Okay, we don't see more questions now. Piotr, yes, I saw that you've already joined our Discord server, so maybe you can also just check it from time to time. Maybe there will be some interesting questions later. But as for now, I think that we can finish. So let me just stop recording.